Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and in this video, I'm going to analyze an active RC filter, in this case, a low-pass filter created with an op-amp.
So let's just look at a little more complicated circuit before we start. Active filters are those circuits that have transistors in them. In our case, the transistors are included in the op-amps. Okay. Back in the day, connections of op-amps were also called analog computers. So you might hear that term. And so what I've got here is a circuit called a biquad state variable Sallen and Key filter. You can see it has 4 operational amplifiers in it. And this particular combination of op amps is designed so that the designer can choose the variables of the resistor to set the gain at a particular frequency. And also, when we talk about filters, we talk about a filter quality called Q. And you want to have high Q values, which tells you about the quality of your filter. And this circuit will also allow the designer to choose values of R's and C's to give you that high Q value. Okay, so this is good. Also, another advantage of this design is that the open loop gain for the op amps doesn't have to be a lot higher than the filter's output gain because of the combination of op amps, and that allows your circuit to get both higher values of gain as well as high values of Q. Let's start with a simpler example. Okay, so here we have an op amp with a minus terminal and a plus terminal, the inverting terminal and the non-inverting terminal. And we have an input Vn, which I've indicated here. Remember, in your mind, you can think of that as a source, an independent voltage source. And we're going to look at the output Vout at the output. Sometimes when you see circuits like this, you will not see this line shown. Okay? And it's just understood that the ground wire is there somewhere. Okay? You might just, it's understood that the ground is how you're measuring everything. So that will be a little bit another way to see a circuit. Okay, so let's look at this circuit in detail. We want to remember a couple of things when we're analyzing operational amplifiers. One is that IN is equal to 0. That's important to remember. And the other is that for circuits with negative feedback, V minus is equal to V plus. Now let's write our nodal equations. So the first thing that we can look at is V plus, and we can notice that V plus is going to be connected to our reference level here, which is going to be our ground. So we know that V plus is equal to 0. At the other node input node, we need to write an equation as well. This one's going to be more complicated. So let's just write it. So the current leaving here will be V minus Vn over R1. We have the current going here, which will be V minus V out over the impedance of that capacitor, which is 1 over SCF. And then we have a current going through here, which is V minus V out over RF. And just to be clear, we also have a current here, but that current we know is 0, right? Because IN is 0. So just for now, I'm going to go ahead and write it in just so you remember it's there. After you get more experience, you will just probably leave that out altogether. Okay, so that gives us an equation that's a little bit messy, but not too bad. So we can rewrite that as V minus Vn over R1 plus V minus V out times SCF, right? The first thing I want to do is get that fraction out of the denominator. And then I have plus V minus minus V out over RF equals 0. So we also know that V minus, I lost a minus sign there. We also know that V minus is equal to V plus, which is equal to 0, right? So I can write that through and I can get 0 minus Vn Let's shift everything up so you can see. 0 minus Vn over R1 plus minus V out times SCF plus minus V out times 1 over RF. Okay, so now we are down to one equation with two unknowns, Vn and V out, and what we're going to be looking for is V out over Vn. So don't forget that. We'll find V out over Vn. So we can take that equation. I have it written here already. If we just multiply through by minus 1, this will be the same equation. I can factor out the V out. So V out times 1 over RF plus SC. And then I move the Vn over R1 to the other side of the equation, which gives us a minus. And now we can write V out over Vn as 1 over R1 over 1 over RF plus SCF with a minus sign in front. Okay, so at this point you could choose to clear your denominators and all that stuff, or you could stop right there. I want to go ahead and rearrange the terms a bit to give us a little bit better understanding of what's going on. So the first thing I did was, sorry, there's a missing minus sign here. There's a minus sign I lost there. So minus 1 over R1, it stays in the numerator. But then the denominator, I go ahead and put SCF, multiply it by RF, and then I have a nice fraction. Okay, and then I can invert that fraction, multiply by 1 over R1. There's that minus sign came back already. We have RF over R1 with the minus over the denominator, 1 plus SRF CF. And if we look at this, what we see is that we have a gain that depends on RF and R1. And that is just the DC gain you would get if you removed the capacitor from the circuit. Remember, at DC, a capacitor looks like an open. We talked about that briefly early in the class. So but you can do it here too. If you're at DC, that would be omega is equal to 0. So if you plug in j omega for S, you would end up with 1 over 1. So you could either remember that at DC, a capacitor looks like an open, or plug in the value. Okay. But what that gives us is a gain of minus RF over R1. So the gain, that is the gain you would get if you remove the capacitor from the circuit. And then we have a component that depends on frequency, and it's 1 over 1 plus SCF RF. And this is the transfer function of a low-pass filter. Okay, we've looked at low-pass filters before, but previously we looked at passive circuits, and now this is active circuit. So a couple of things to realize, that this gain, I just said this, the gain is equal to minus RF over R1, and that's just the DC gain. And the low-pass filter is going to have a corner frequency, okay? And that corner frequency occurs when the gain is below minus 3 dBs, and we can set this corner frequency independently of the gain because we've got that capacitor CF, and we can choose that. So you can set the overall DC gain using RF and R1, choose your capacitor to put the corner frequency where you want it. Here's some simple MATLAB code. I like to go ahead and write my terms at the top so that I can easily change them out if I want to see what happens for a different value. So then I can define the numerator to be minus RF over R1, the denominator to be CF RF times S plus 1. And then I can plot using freq S, the numerator over the denominator. So let's go back for a moment. So this is 1 plus SCF RF. So when I write this is the times S to the 0 term. This one is the times S to the 1 term. So it's important to always put the highest order coefficients on the left side of that. Okay, plot it. We end up with this nice frequency response plot. Looks like kind of like some of the ones we got with passive filters. Again, I want to remind you that this is a log-log plot on the magnitude. So this value is 10 to the 1. So we have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Okay, going up the side, we have 10 to the 0, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we can find the 3 dB down point. Basically, we look at this. This is where it's flat at the top, which is around 10 to the 1. 3 dBs down would be 7. Okay, let's go ahead and look at that a little bit. 1, 2, 3, 4, 5, 6, 7. So that is 7, which is 3 dB less than 10. Then I can look down here, and I can see that that corner frequency is at 100 radians per second. Okay. We can also look at the phase plot. The phase plot is semilog, so again we have log along the x-axis, and then along the y-axis we have the phase in degrees, because that's how I plotted it. So 80, 90, 100, 110, 120, all the way up to 180. So you can, at any particular frequency, figure out what the phase shift is if you like as well. Okay, but the corner frequency is determined by the 3 dB down point on the magnitude.